Welcome to Ask and Learn.
In this problem, we have an electric motor turning an eccentric flywheel with an equivalent, which is equivalent to an unbalanced quarter-pound weight located 10 inches from their axis of rotation. We're told that static deflection of the beam and the motor weighs 150 pounds. And we neglect the mass of the beam compared to the weight of the motor. So the static deflection is the weight of the motor, 150 pounds, divided by the spring constant is the weight of the motor divided by the static deflection. So this is the static weight of the motor. The static weight of the static deflection, in this case we were told was 1 inch, so 1 over 12 feet. So we get a spring constant of 1,800 pounds per foot. Now we can find the natural frequency just by, if we know the spring constant and we know the mass from W, so the mass is W over G. So our natural frequency becomes 19.7 radians per second. And in the first case, they wanted us to figure out the angular velocity when resonance occurs. Well, resonance occurs when the angular velocity, or the excitation frequency, is the natural frequency. So when the excitation frequency is 19.7 radians per second. And let me actually calculate that in RPM for you. So 19.7 times 60 divided by 2 pi is 188 RPM. So that would be how fast the motor would be spinning if the system were to be excited into resonance. So that's usually something you want to avoid. So you want to avoid having the motor spinning at this speed for any length of time anyway.